The symbol for acceleration is a lowercase a. The equation for acceleration is the change in velocity over change in time. That is a boxed equation. Reviewing, that means you will get it on a quiz or final exam. It will be provided for you. Okay. What does delta V mean mathematically? Delta V means mathematically what? Spencer? Change of velocity, that would be those would be the words. Absolutely, change of velocity for the math. What's the equation for delta V? Trevor? Delta means change in. It always means the final minus initial. In this particular case, delta V, the change in velocity means velocity final minus velocity initial. Therefore, on the bottom we have delta T. That is going to be the change in time, or the time final minus time initial. What dimensions do we get for acceleration? Acceleration, Pieper dimension. How do you get that? Walk me through it. Let's start with the dimensions for velocity, people. Divided by the dimensions for time. I'm going to put seconds over 1, because seconds and seconds over 1 are the same thing, which reminds us that we class need to
Flip the guy and multiply.
Flip the guy and multiply. Who's the guy? Seconds over 1. So this is the same thing as meters per second multiplied by 1 over seconds. And therefore we get that acceleration is in meters per second squared. We could, of course, have kilometers per hour squared, furlongs per fortnight squared, for example, but meters per second squared is really pretty much all we work with for acceleration. Bless you. Please be aware that acceleration, just like displacement, just like velocity, has both. There you go. Magnitude and direction. Magnitude meaning the amount of meters per second squared, and direction simply meaning the direction. All right, so let's go through a simple example. Let's say that I'm driving my, and I know this is going to shock many of you to discover that I drive a black Toyota Prius. No, it's shocking, true. I'm driving my black Toyota Prius eastward at 9.0 meters per second when I see a deer. And I stop in 5.0 seconds. No deer were harmed in the creation of this example problem. The deer makes it out alive. It's fine. Just a side note, over Labor Day weekend, I went to Wheeling, West Virginia for a family reunion for my wife's side. 40 people got together. And in Wheeling, West Virginia, the deer are like squirrels. It was amazing. They're like right next to your cabin, asking for food. You walk up, it's like, can't quite get close enough to it because it'll skitter away like a squirrel, but still, it'll like walk up to you, like right next to you and try to take your food. It's weird. Okay. All right, so I apologize. We're looking for the acceleration, please. What is the acceleration of the car? So I see the deer moving eastward at 9.0 meters per second. I see the deer and I stop in 2.5 seconds. What do we do now, please? Keisha? Sorry, Keishiro. Keishiro. Acceleration. Good, keep going.
The velocity is 9.0 meters per second.
Keep going.
Time is 5 seconds.
Shouldn't the change in velocity be 0 because your final velocity is 0 because you stopped, so it'd be 0 minus 9.
Remember, change in delta always means final minus initial. So this is velocity final minus velocity initial, divided by the change in time. Now, this 5 seconds is our change in time because it's not a time initial or a time final, it's the time duration. So we do need on the bottom our change in time of 5 seconds. But the acceleration then is equal to 0 minus 9 divided by 5. You have to be very careful with that. It is often that students forget that little piece. Eric?
If we wrote just negative 9.0 and didn't show that it was 0 minus 9, is that wrong?
Yes. You got, I mean, like, you've got to show why, like where that negative came from. Otherwise, it's just a negative. You have to start with your equation. You have to fill in the stuff. Now, in your math class, you would leave this as negative 9/5. This is not your math class. This is your physics class. In physics, we're going to not leave things in fractions because we're interested in what the numbers mean. And fractions are harder to identify what the numbers are. So the acceleration then is equal to what? Tina? So then the acceleration is negative 1.8 meters per second squared.
Read the empty square.
Frank? We do. We have correct number of sig figs, 9.0, 5.8, 5.0, and so 1.8. We have just 2 sig figs. Eric?
Do we need eastward?
Do we? That is a great question. Does acceleration have both magnitude and direction, class?
Yeah.
So do we need eastward? Yes, we do. We have the correct number of sig figs, we have the correct dimensions, but we forgot the direction, so eastward. So the acceleration is negative 1.8 meters per second squared east.
They use direction in the book.
I'm sorry, could you say that again?
They don't use direction.
Ah, that's a good statement. You will discover also that they don't distinguish between velocity and speed very well. We will highlight things that the book does wrong from time to time just for fun.
Quick question about that.
Your shot.
Why did you have 0.8 right there and you had 2 no, wait. It was on the last
Oh, I hear your question. Keep going.
It was, you had 2 sig figs and the answer is 270.
Fair enough. Let's start here. So in the question, the distance total was given as 1,600 meters, correct? So what I did is we converted that over to get the distance total was equal to 1.6 kilometers, right? And we figured out that distance 1 was 0.8 kilometers, right? All right. And he asked the question, why didn't I simply have 1 sig fig in my answer, right? That's your question. It's a good question. Right. I agree with that, but I need a little more. Eric?
Because it wasn't a given, 0.8.
It's not a given, right?
Okay.
So as I'm going through the problem, there's no right reason for me to write 0.80 every time. Because when you're trying to figure out sig figs, you just go back to the very beginning. So you go back to the givens. This was a given. This is something we derived from the givens. So there's no reason to like write out all of that when we're working on it. Good?
Okay.
All right.
Thank you.
You're welcome.